Good morning, all. Myself, Mukesh Asati, giving you a brief introduction about discrete structure. In discrete structure, we study about set, theory, relation, function, mapping. So, first of all, we start from what is a set. A set is a well-defined collection of distinct objects, or we can say that distinct elements, because in a set, no elements would be duplicate, or we can say that every element have its uniqueness or unitivity. Now we can say a set consists of letters, symbols, elements. Now we have category of sets as countable and uncountable sets. Suppose we say that a set of natural numbers. Set of natural number means the elements of natural numbers like starting from 1, 2, 3, 4, 5. So these are elements of natural numbers. So if a natural number set starting from capital N denoted by capital N would be started from curly bracket and end with curly bracket and having elements of starting from 1 to infinity. Now, if uncountable sets, if we have too many elements such as real numbers from 0 and 1, what is the composition of relations? When two relations to form new one by linking elements through an intermediate set, we have various operations to perform on sets, pictorial representations of set, and we say that Venn diagrams. And equivalence relations, partitions are set into classes of equivalent elements characterized by being reflexive, symmetric, and transitive. Partial orderings arrange elements with a reflexive, antisymmetric, and transitive relation. This presentation covered essential concepts in set theory and relations, including definitions, classifications, and visual tools. Understanding countable sets, Venn diagrams, and various types of relations enables deeper insights into mathematical structures and practical problems such as scheduling. In Venn diagrams, we represent operations on sets performed on one or more two sets like union, intersection, difference, complement. Now, if we talk about a function is a relationship where each input has a unique output classified by types like one to one, onto, and into, surjective, bijective. An inverse function exists for a one-to-one and onto function, while the composition of functions combine two functions. Recursively defined functions use previous terms to define new ones. The pigeonhole principles states that if you have more pigeon than pigeonholes, it means if we have more pigeons, which are called objects, and we have less boxes in which we have to put pigeons, then the pigeonhole principle states that if you have more pigeons than pigeonholes, at least one pigeonhole must contain more than one pigeon. Suppose we have 13 employees and having date of birth. So we know that if a year have 12 months and we have 13 employees, it means two of the employee have same birth in the same month. So here number of pigeons we have 13 and number of pigeons holes we have 12, so that at least two pigeons occupy one box or one pigeonhole or 1 month. Now function types: one to one, injective, onto, surjective, into, and bijective. In one to one injective, each element in the domain maps to a unique element in the codomain. No two different inputs produce the same output. Every input produces every individual output. In onto surjective, every element in the codomain has at least one corresponding element in the domain. The range is equal to the codomain. In into, every element in the domain maps to a unique element in the codomain, but not all elements in the codomain are necessarily used. There is at least one element in the codomain that is not an output. A function that is both one to one and onto. Here we have taken an example of pigeonhole principle. Again, if there are n items to be put into m containers with n greater than mn is greater than m. If you have 13 people, at least 2 of them must share the same birth month. What example I have taken previously. Now, if we talk about mathematical induction and proof by contradiction are two different methods for proving mathematical statements. Mathematical induction is used to provide statements about all natural numbers by proving a base case and an inductive step, which shows that if the statement is true for one number, it is also true for the next number. Proof by contradiction is an indirect method where you assume the opposite of what you want to prove is true and show that this assumption leads to a logical contradiction, thus proving the original statement must be true. Here there is a methodology what we are doing in mathematical induction. Firstly, what is the purpose? To prove a statement is true for all natural numbers. Then method, a two-part process. Base case, first we have to prove that it is equal to for n equals to 1. Then second, inductive step, here we prove that it is also true for k plus 1. Then analogy, like we have to prove all it is true for m plus 1. Now for proof for contradiction. To prove a statement is true by showing its opposite is false. A three-part process. Assume the opposite. Start by assuming the statement you want to prove is false. Derive a contradiction. Follow logical steps from the assumption until you reach and derive a contradiction, where we have to follow logical steps from this assumption until you reach a result that is impossible or contradicts a known fact. Conclude the original statement whether it is true or false, since the assumption of falsehood leads to an absurd result. Now for analogy, to prove something is true, you try to show that a world where it is false cannot logically connect or exist. Thank you.